Hello, everyone. This is Gauthaman, a fourth year PhD student from Georgia Institute of Technology. So in this presentation, I'll be presenting about a 3D PNR flow involving reinforcement learning based parameter tuning to optimize the performance of 3D placement engines. So before getting into the details of our research, first I wanted to start with a slight background on the current status of 3D physical design methodologies. As of now, we have several pseudo 3D flows that are developed for efficient physical design of 3D ICs like Shrunk 2D, Compact 2D, Withpin 3D, and Snap 3D that were designed in our labs. But an issue with these pseudo 3D approaches is that they pose 3D placement as a 2D problem. So what happens here is an initial 2D placement is transformed into 3D placement using partitioning techniques. But while doing so, a lot of 3D nets in the design undergo degradation. But still, these pseudo 3D flows compensate this 3D net degradation by using commercial routing and optimization tools. So despite this 3D degradation, if pseudo 3D tools can offer such great PPA improvements over 2D design, what would happen if we used true 3D placement approaches with commercial routing and optimization tools? And that's the main idea behind our research. A lot of research has happened in this field of 3D placement, and I have listed some of the academic 3D placement works in this slide. We have Force 3D developed in our lab, which is a force-directed 3D placer. And there is Nonlinear 3D from UCLA, ePlace 3D from UCSD, and TSV-aware 3D placer from NTU, which are analytical 3D placers. So instead of reinventing the wheel, we obtained source codes of Force 3D, NL3D, and ePlace 3D, and we performed an initial preliminary research to identify which works can be extended further. Among these three 3D places, the NL3D placer offered slight wavelength improvements, and so we use the NL3D placer as the main 3D placement engine in our work. So how is our work different from some of the state-of-the-art 3D flows? The key idea of our work is to perform true 3D placement and then use cell width shrinking to perform clock tree synthesis and optimization in a 3D fashion. So the main strength of our work is that it offers best performance, power delay product, and energy delay product than the other three 3D flows. So the striking difference, as I mentioned earlier, comes with respect to the placement. The state-of-the-art 3D flows use commercial engines, commercial 2D engines, and use tier partitioning techniques to perform placement. But we use true 3D placer, which is enhanced using reinforcement learning to perform placement. And when it comes to legalization, both Shrunk 2D and Compact 2D within 3D flow perform die-by-die legalization. So the scope of improvement or scope of optimization is highly restricted here. Whereas both Snap 3D and our work optimize considering all the tiers together. And in our 3D design, we restrict the number of tiers to 2 because of the limitation in the commercial 2D tools. Next, if you look at signal routing and clock tree synthesis, we perform both of these in a 3D fashion using the commercial 2D tools. And finally, we perform post-routing optimization using enhanced die-by-die technique, which is also used in Pin 3D flow. So when I say enhanced die-by-die technique, the commercial tool is aware of the entire 3D design, but at a given time, it only optimizes a particular tier while fixing the cells belonging to the other tier. Here is an overview of the Art3D flow. So in Art3D, we tune the parameters of the NL3D places to obtain the best PPA result. So the training sequence mainly goes as we pick several netlists and perform a two-tier 3D placement on that by tuning the placement parameters in the NL3D placer. And once we obtain the two-tier 3D placement, we combine the tiers together by shrinking all the standard cells and then we perform placement legalization and clock tree synthesis. Followed by that, we restore the cell width back to the original sizes and we perform global routing on each tier. So we then estimate the PPA of this global routed design and use it for the training purpose. After running several iterations, when a significant amount of PPA improvement has been achieved, the model is assumed to be trained, and based on the best result obtained so far, we go for the next stages of the design, like performing detailed routing and then timing closure. So in case of inferencing, we just directly use this trained model and then perform the entire PNR flow starting from placement till the timing closure. If we look at the setup of our 3D flow, as I mentioned earlier, we perform two-tier 3D design because of the limitation in the commercial 2D tools. And the true 3D placement engine, that is the NL3D placer, does not support standard Verilog format. Rather, it uses a format called as bookshelf. So we build an interface which converts the Verilog format into an intermediate format that is based on design exchange format and library exchange format, and then we convert it to bookshelf. We use this intermediate format because we have standard converting tools that convert codes from Verilog to DEF and LEF, and those that convert from DEF, LEF to bookshelf. Next, we set up some 3D technology files for the commercial router. We create 3D LEF files which contain the physical information of 3D routing stack, and we create 3D LIV files which contain timing information of standard cells belonging to both tiers. Next, let us get into the details of our true 3D placement engine. So we use NL3D Placer as our main 3D placement engine, which is an analytical 3D placement work developed by UCLA. So the objective function of this 3D placement engine is to find the X, Y, and Z locations of a cell I such that it minimizes the net length of all the nets connecting the cell I. So as opposed to a 2D placement objective function, the 3D placement objective function considers all three dimensions X, Y, and Z. And also, when we represent the wire length of nets in this objective function, we not only consider the half perimeter wire length, but we also consider the number of MIBs in the nets. So in case of a 2D net which connects cells present in a particular tier, the number of MIBs on that net is 0. And in case of a 3D net which connects cells belonging to different tiers, the number of MIB on that net is 1. So even 3D nets are accurately represented in the objective function of 3D places. So while minimizing this objective function, more weightage can be given either to the half perimeter wire length or to the number of MIBs in the design. So these are two of the placement parameters that are present in this placement engine. And apart from these, there are also several other placement parameters which can be tuned, and I'll be talking about them in future slides. So this objective function is solved using nonlinear programming technique, and hence we call this placer as nonlinear 3D placer. But as I mentioned, there is an issue in this placer because the placement quality highly depends on how these placement parameters are tuned. And unless we configure these parameters in an intelligent manner, the placement quality of true 3D engines is not going to beat the placement quality of pseudo 3D engines. So we tune these placement parameters using the reinforcement learning framework shown here. We first define a set of placement parameters for any given netlist, and we call that as a state. And the RL agent performs an action on that state, that is, it tunes these placement parameters, and then it configures the NL3D placement engine. Then we perform true 3D placement using this NL3D placer, following which we also perform signal routing and optimization using the commercial router tool. After signal routing and optimization, we obtain the PPA results, and we use those PPA results to compute a reward function. So as it can be seen from this equation, we use wire length and verse negative slack and the power values obtained from the 3D physical design flow. And we use this weighted sum to encapsulate these different PPA metrics into a single metric. And it can also be seen that we provide more weightage to the verse negative slack and total design power than the wire length. That is because the main focus in our 3D physical design work is to improve the verse negative slack so that we can also improve the effective frequency of the 3D ICs and also to improve the overall power of the IC. So once we have this reward, the RL agent uses it to evaluate how good the placement parameters were. So based on this reward, it again configures the placement parameters and generates a new set of parameters and configures the NL3D placer, and this entire training sequence continues. These are the placement parameters that we tune using the RL agent. We tune the number of placement bins in each X and Y direction, as the number of grids in the design greatly affects the placement quality. Then there are a few parameters that correspond to the clustering that happens during initial placement, and we tune those as well. And as we saw in the objective function, we have two weight parameters, that is the wire weight and then via weight, and we tune those parameters as well. Then there is a parameter that corresponds to the maximum cell overlap allowed to terminate detailed placement. And there is a parameter that controls the maximum density percentage that is allowed in each placement bin, and we tune those as well. And there are a few additional parameters that correspond to the smoothing functions that are used in the NL3D placer to accurately depict the wire length and to smoothen the bin density. And we tune those parameters as well. And finally, there are a few placement parameters which, when tuned, can deal with routing congestion in any netlist, and we tune those parameters as well. So how does the RL agent tune these placement parameters? The RL agent uses a scheme called as multi-armed bandit or MAB technique, which consists of a set of search techniques in it. And so the main goal of this RL framework is to find a parameter setting such that the reward obtained is maximized for a given netlist. So what happens in this case is using the MAB scheme, multiple search techniques are used to configure the placement parameters. Like in our case, we run around 10 to 15 parameter search iterations, and in each search iterations, we run around 5 placement and routing runs. So in each search iteration, using multiple search techniques, a search engine first configures the placement parameters. And using these configured placement parameters, we run the PNR flow and we generate a reward, as I mentioned in the previous slide. And a reward measurement engine measures this reward and associates it with the corresponding search technique used for manipulating the parameters. Now, this search engine again reads this reward, and it maintains a history of the search technique used and the reward obtained. And based on the reward, it assigns a credit to each of the search techniques used. So if any search technique gets a very high credit, then it uses that search technique while performing parameter tuning in the next stage. And this is called as the exploitation phase. That is, it exploits the search technique which is capable of producing the best or a better parameter configuration. But if none of these search techniques achieve a higher reward or achieve a higher credit, then the search engine uses again multiple search techniques like an Elder-Mead or differential evolution technique to again create another set of 5 placement parameters, and this training sequence continues. And this kind of training is called as exploration-based training. So our RL agent decides or chooses a search technique based on this equation, and it selects between the exploitation phase and exploration phase. So as I mentioned earlier, we run around 10 to 15 parameter search, so which is around 50 to 75 PNR runs. And at the end of these PNR runs, we find a parameter setting that works best for a given netlist. We train our RL agent using some of the standard benchmarks. Like we use a cell dominant benchmark AES-128, and we use a net dominant benchmark like LTPC, and a hard macro based benchmark like RocketGo to train our RL agent. So after these 50 to 75 PNR runs, we obtain train parameters for these 3 different kinds of benchmarks. And if you look at these trained parameters, for cell-dominant benchmarks, we can observe that the parameters help in cell spreading to avoid placement and routing congestion. And for net-dominant benchmarks, the parameters help in optimizing wire length by avoiding routing congestion. And in macro-based benchmarks, where we have large hard macros, these parameters help in avoiding placement and routing congestion around these large hard macros. So now that we have a RL-based NL3D placer with which we generate high quality true 3D placement, we also need to make sure that the benefits of this true 3D placement are propagated until the end of the physical design flow. So we need robust backend routing and optimizing methodologies to propagate these benefits. So for this purpose, we design a routing methodology using commercial 2D PNR tools, and we use 2 different flows to perform placement optimization, clock tree synthesis, and then final signal routing and timing closure. So first we use a flow called as shrunk 3D, in which we use half-width cells and 3D tech files. So the reason behind using half-width cells is that 2D tools do not support a placement density which is greater than 100%. So to avoid this issue, we reduce the width of the cells, but at the same time, we retain the pin location of the cells at their original location and at their original tiers, that is for both top and bottom tiers. So using this modified cell width and using 3D routing stack, we perform placement optimization and clock tree synthesis using this shrunk 3D flow. And after clock tree synthesis, we again restore the cell width to their original sizes, and then we continue to perform signal routing and timing closure using Pin3D approach. And we used enhanced die-by-die technique to perform post-routing optimization to achieve timing closure. So we first trained the RL model in our 3D flow using several 28 nanometer and 16 nanometer benchmarks. And in the following slides, we present the results of some of these circuits used for training and 2 circuits we used for inferencing. We evaluate our 3D flow using PPA analysis, critical path analysis, clock metric analysis, and memory net analysis. First, we compare the performance of our 3D flow with some of the state-of-the-art 3D flows like Pin3D and Snap3D. We use published results for this comparison, and on an average, we see that the R3D flow improves total power and power delay product by up to 5 to 10% over the state-of-the-art 3D flows. Next, we compare the performance of R3D with the baseline 2D flow and a 3D flow involving manual parameter tuning of the NL3D placer. So for this purpose, we used various 16 nanometer and 28 nanometer benchmarks, and we have presented the results of some of the benchmarks used in this slide. Again, we can see that R3D flow provides the best total power and power delay product compared to the other two flows. And on an average, we see an effective frequency improvement of up to 25% over the 2D flow. And the total power improves by almost 31% over the 2D flow, giving an effective improvement of 43% in the PDP. And similarly, R3D flow improves the power and PDP by almost up to 12% over the 3D flow involving manual parameter tuning of an L3D placer. And it is also to be noted that R3D flow improves the effective frequency by almost up to 25% over the 2D flow in case of processor benchmarks like Cortex A53 and A7. So next we present critical path, clock metric, and then memory net analysis between 2D and the R3D flow using 28 nanometer Cortex A53 benchmark. So if you look at the critical path analysis, R3D provides better critical path delay, like by reducing the critical path delay by up to 10%. Next, if we look into the clock metric analysis, we see that R3D offers better clock latency, but however, the clock skew, clock wire length, and the number of clock buffers used are higher than the 2D design. But the reason behind using higher number of clock buffers in case of R3D flow is that to improve the worst negative slack, a lot of buffering is required, and hence we see such a drastic increase in the number of clock buffers used. And finally, R3D also offers better memory latency, memory path length, and memory access power compared to the 2D flow. To summarize, our work involves a 3D PNR flow with true 3D placement engine, and we optimize this true 3D placement engine using RL-based parameter tuning. Our R3D flow offers better effective frequency and lower total power, thereby giving highly optimized power delay product over the 2D and the state-of-the-art 3D flows.